At the American Museum of Natural History studies bats, their incredible diversity, and their evolution. She talked to Siam's 60-Second Science about a recent discovery that has finally brought an end to a long-standing mystery about how bats evolved.
The fossil record of bats is an interesting one because we have both great riches and great gaps in our knowledge. Starting in about the 1960s, we began in a couple of parts of the world to find some really nice complete bat skeletons that were very old, dating back to the Eocene, about 52 million years ago. Icaronecturus was the first one to be discovered, and this was described in 1966. And one of the most amazing things about Icaronecturus is that it's basically just like a living bat. It's 52 million years old, but it has the long fingers. It has the specializations of the shoulders and the rib cage that make it clear that it could fly. An examination of the skull indicates that it probably could echolocate too, that it has various features in the ear region that seem to go along with receiving echolocation calls when we look at the living bats. So we've been left with this quandary as to which came first. Did echolocation evolve first, or did flight evolve first, or did they evolve at the same time? And because the oldest known, most primitive bats, that is Icaronecturus, had both of these features, we had no way of answering this question. It was just one of the great unknowns of bat biology and evolution. Where did bats come from? We didn't know. The first bat in the fossil record looks more or less, probably if it was alive flying around right now in my office, it would look just like a regular modern bat. So this was one of the great questions up until quite recently, when we found two specimens of a new species, which we named Onychonecturus, just this year in 2008. Onychonecturus is from the same rock beds as Icaronecturus, so it's the same age, it's 52 million years old, but it's much more primitive in its anatomy in some really important ways. Starting with the anatomy of the wings, it preserves small claws on each one of its fingers, whereas Icaronecturus lacked claws on several of its fingers. So we knew just in a first glance at this animal that it was new and different and exciting and more primitive. However, first glance at this animal also told us that it was a bat. It has those long fingers. It has the specializations of the shoulders that made it clear that it could fly. So here is another slightly more primitive bat. It could also fly. Well, what about echolocation? One of the very exciting things about this animal is that there are two specimens, and one of them is well preserved enough for us to be able to study the ear region. And we found by looking at the ear region that Onychonecturus probably could not echolocate. So here we have a primitive bat that could fly but not echolocate. So it looks, from examining these animals and comparing them in the context of an evolutionary tree, basically a family tree of bats, that flight evolved first and echolocation only later. So this has answered one of these big, long-standing questions. In essence, discovering a new fossil has given us the answer to this question.
It's just pretty interesting to be carrying these fossils to another room.
What I have here is the best preserved specimens of the two oldest bats, so Icaronecturus and Onychonecturus. And the one on top here is Icaronecturus. It was described in the 1960s, and this specimen belongs to Yale University. They were kind enough to loan it to me. But we have to pack these very carefully so that we protect the specimens adequately, so nothing can happen to them because they're completely irreplaceable. So this is 52.5 million years old. And this is the bat I was discussing earlier, that basically if it was alive today and flying around, it would be very hard to tell apart from other living bats today. It could fly, it could echolocate, its wing proportions are very similar to many living bats. One of the most remarkable things about this specimen to me, I had never seen this animal or seen this specimen until a couple of months ago. I'd seen many, many photographs of it, but when I went to Yale to pick this up and I turned it over, I was astonished to find this that has been prepared on both sides, and you can actually see through it in places. So we can see both sides of the skeleton, parts of the skeleton here, which has been very useful. And this is Onychnicterus. There are two known specimens, and this one actually belongs to a private individual who was kind enough to loan it to us for scientific study so that it could be part of our description of this new species. So there's one specimen that belongs to the Royal Ontario Museum that we based our description on, but this one shows us parts of the skeleton that we couldn't see on the other one. Well, you can see the little claws on the tips of each of the fingers here, and it's kind of hard to see on that one, but that one lacks the claws on these three fingers. The hind legs are much larger here than an Onychnicterus, and the forearm is proportionately shorter. So when you look, if you take the long fingers off this in your mind, if you look at just the limb elements, it looks a lot more like a terrestrial mammal in its overall limb proportions. Onychnicterus, on the other hand, even if you take the fingers off, you see these great long forearms and these tiny little hind legs, which make it look quite different from a terrestrial mammal.